Alrighty, so next lesson that we're going to look through is how to use these four representations to solve certain problems. Well, specifically the three mathematical representations for these linear relations. So I'm just going to go through a few problems, show you how the different representations get used to answer questions, and then we'll talk about which one's best, sort of thing. Holton's doing a charity walkathon here. He's raised a certain amount of donations and has had other people pledge an amount per kilometer he walks. So some people have handed him money, and some people have said, well, I'll give you 50 cents for every kilometer you walk, something like that. And some people have just said, here's 20 bucks, please leave me alone, and they're not worried about how many kilometers he walks. So the equation is 12x plus 50, where y is the amount raised and x is the number of kilometers he walks. So I just want to take a second and break down what that means. So the initial value is the 50. That's the initial value. That would be the amount that he's already raised. So that's the cash that he has in hand already. And then the rate of change is that 12. And that would be the pledges that he's gathered. He's earning $12 every kilometer he walks. How far does he need to walk in order to raise a total of 200? Well, it's an equation. 200 is one of the variables in the equation. You just got to pay attention to which one's which. Y is the amount raised. 200 is an amount raised. So 200 is going to be the y value in this equation. So what we can do is replace y with 200. Leave everything the same. And oh my goodness, we've solved 100 of these before. So get rid of that 50. Divide by the 12. And 150 divided by 12 is 12 point something. 12.5. So he needs to walk 12.5 kilometers in order to raise the total of 200. Okay, so that's how we use an equation. I've got another equation example later. But here we're going to work with a table of values. So create a table of values in order to solve this problem. Tessa's Ice Cream Shop charges $3 for a sundae and 15 cents for each topping. So number of toppings and cost. And so $3 again, that's the starting cost, that's the initial value. 15 cents, that's the rate of change. It goes up 15 cents every time. So when you do your table, I always want you to start off again at 0 so that you see the initial value of $3. And our first problem, we're going to figure out how much it costs for 4 toppings. So we'll just count it up to 4. So $3.15, $3.30, $3.45, $3.60. So there's the answer to our first question, $3.60. Now the next one, how many toppings could you get if you had $5? Well, we just have to kind of keep going until we reach $5, and it's going to take a while. If I count up 15 cents at a time, I kind of get the sense that it's that it's going to take me a while. So maybe I'll start jump counting. So from 6, I can go up to 8. So go up by 2 toppings. And I just need to remember that's going to go up 30 cents at a time now instead of 15 cents. 4.50. If I go up 30 cents, another 2 toppings, another 30 cents. Oh, that's getting close. So I'll slow down again. I'll just go up 1 topping, 4.95. And then for this type of question, I do like to go past the $5 to prove that the next one goes over. So the next one would be $5.10. So then I can tell you, if you got $5, you can get 13 toppings. So again, table of values, nice way to solve it. Just remember, if you need to go way down the table, it makes sense to start skip counting. But again, if it was a different type of problem and we had to go up to like 100, it wouldn't be toppings on an ice cream sundae, but if we had to go up to 100, maybe table values wouldn't be the best way to solve this problem. Okay. So create a graph in order to solve the following problem. I've given you this. This is going to be the amount of fuel they have on this axis. That's a weird place to label it, but I labeled it up there. And this is number of hours. So I'll add those labels to our graph. They start with 57 liters, so that's going to be our initial value. We're going to start the graph up there. And then every hour that they drive, they use 6. So we're going to go down 6. So our rate of change will be -6. So just pay attention to your scale. So 1 hour is here on the graph, and we're going down 6, so down to 51. And then another hour, down 6, down to 45, down 6, down 6. So again, just paying attention to the numbers on the scale. The grid was already set up for us nicely. And then that one would hit below there if I'm following that pattern. All right. There we go. Missed my last stop. So how much fuel is left in the tank after 6 hours? Now we're actually going to use this to answer the question. So I'm going to look at 6 hours and see that there is, that one's 21 liters in the tank. When will they run out of gas? So we got to follow along. When do they hit bottom? It should be right there where they run out of gas. They have 0 fuel left in the tank. So remember, that's on the axis there. So this is 9, that's 10. So it should be right on 9.5 hours if you had your ruler in the right spot. There we go. So graph, very nice if the numbers work out nice. If you can see exactly where the points are that you want on the grid, really easy to do. But if I had to set up this graph and label all these values on the axes, it probably would have taken me much longer. But if you've got a perfect grid set up, then it's a really nice tool to solve problems with. But again, if they were using 5.3 liters of fuel every hour, it would be kind of a pain to graph something like that. So in the right situation, a graph could be really nice to use, but it's not always the right situation. And finally, the equation. Create an equation in order to solve the following problem. Ben works for a tree care company. They pay him $400 for the week plus $237.50 for every tree he cuts down. So here's an example where like trying to graph this one would be quite a pain with that rate of change there. So again, identifying which one's the rate of change. This is kind of a weird example where they both kind of look like rates. It's 400 per week plus 237 per tree. The key here is if you read through the problem, it's asking us about how many trees. So trees is the thing that we're going to keep track of. So that makes the cost per tree the rate of change. And we're going to treat the 400 like just a starting amount. He starts with 400. And then he gains extra every tree he cuts down. So how much does he earn if he cuts down 5 trees? So create an equation in order to solve this. So remember, for an equation, you need a variable. So I'm going to say his pay for P equals, you put the rate of change with the variable, which is going to be the number of trees, and then you add the initial value after the fact. So there's 2 terms. One of them has a variable, that's the rate of change. One of them doesn't have a variable, that'll be where the initial value goes. How much does he earn if he cuts down 5 trees? So for part A, it's telling me a number, it's telling me the N. So I'm going to say P equals 237.50 times 5 plus 400. And that is multiplication, so I'm going to do 237.50 times 5 is $1,187.50. And then I'm going to add the $400 that he has to start out and get that as his total pay for that week if he cuts down 5. Part B is the other type of question. So instead of telling us the n value, how many trees must he cut down, it's asking us to find n in order to earn 3,000. It's telling me that his pay, so I can put that in for pay. And we can solve this equation. So the first thing we're going to do, it's a simple one variable in the equation. We're going to get that variable by itself. We'll get rid of the 400 first. And then divide by the number in front of n. And I get 10.9. So what that means is he would have to cut down 10.9, 10 and a bit trees in order to reach exactly 3,000. So that means, therefore, he must cut down 11 trees to reach his goal of $3,000. Now, even if that came out as 10.001 trees, even though it's so close to 10, what that's saying, if it's 10 point anything, it's saying that 10 trees isn't quite enough. So in this type of problem, if you're trying to reach a certain amount, you always have to kind of round that up. So you just got to pay attention to the context. That means 10 trees. If it's above 10, 10's not enough. You got to go up to the 11th tree. And again, if it was, you wouldn't leave it as a decimal here because it wouldn't make sense to leave it as a decimal in this case. But that's one where you'd always round up because it means 10's not quite enough. Okay, so that's using an equation to solve a problem. We actually solved 2 different problems there. What I want you to see, what the whole point of this lesson is I want you to realize that the equation's a really powerful tool because this one had the worst kind of numbers involved in it, and we solved it relatively quickly. And it doesn't matter how complicated the question is, or even if this answer, instead of 10 trees, if it was 600 trees, it would have taken us those exact same amount of time, the exact same steps. Get rid of that, divide by that. It would have been the same no matter how ugly the numbers are. So the equation is sort of the tool that you should look for because, well, we put all that work into algebra, we might as well put it to use. But it always doesn't matter how ugly the numbers are, it always takes the same amount of time, and that amount of time is not very much. Setting up a graph can take a lot of time, and it only works out nicely if the numbers happen to be nice. Table of values, super easy to use, but again, if you have to go really far down the line, if the answer is going to be 100 something, like the 100th thing in your table, it's going to take you a long time to get there. And obviously, you're kind of counting by certain amounts. It's easy enough to make a mistake doing that, but the equation, again, it's always at most these 2 steps to get there. So the equation is kind of the powerful thing. So in the practice down here, again, I'll post my solutions to it so that you can check your work. But go through these, and then you can use any of the types of things. You can use equation, graph, table, doesn't matter which one you use, but see if you can solve those problems with one of the representations.